Most standard language agents operate with a severe design flaw. They treat conversational history as transient scratchpad data. They collect information during a chat, execute their reasoning, and dissolve the moment the session ends. The agent wakes up to every new conversation with complete amnesia. This chart tracks context window usage over a single continuous session. To solve the amnesia problem, developers often force the agent to retain every previous message. As the conversation stretches on, the token count grows monotonically. Eventually, it hits the hard limit of the model's context window, and the execution chain breaks. The standard industry patch for this is naive RAG. Instead of keeping everything in the active context window, developers dump raw chat history into a persistent vector database, retrieving older messages based on semantic similarity. But running raw history dumps in production introduces two massive points of failure. First, querying a database directly inside the interactive loop comes at the cost of high latency. Second, users frequently change their minds. When you retrieve raw history, the model pulls outdated facts that conflict with current instructions, paralyzing its reasoning logic. If gaining persistent memory degrades inference speed and reasoning accuracy, enterprise LLM applications cannot scale past basic demonstration environments. LangMem corrects this by splitting the memory architecture. It formally decouples agent memory operations into two distinct complementary operational planes. The first plane is the hot path. This is a highly constrained, synchronous loop that runs actively while the user is waiting for a response. It handles targeted, real-time memory reads and writes, moving fast enough to maintain conversational latency. Beneath that is the cold path. This is a heavier, asynchronous background environment where offline workers extract insights, resolve conflicting facts, and distill knowledge long after the active conversation has finished. By pushing heavy distillation out of the interactive cycle, LangMem creates persistent, long-term memory structures without adding milliseconds to the live reasoning loop. The hot path strictly governs what happens while the agent formulates a reply. It begins the exact millisecond a user sends a message. Before the reasoning cycle even initiates, a memory searcher queries the base store. It scans for semantically relevant memories tied to that specific user and injects those precise parameters directly into the system prompt context. Once reasoning begins, the model evaluates the current turn. If the model detects a new user preference or a procedural fact that it will need later, it triggers an in-loop memory manipulation. It does this using a specific tool primitive called create-manage-memory-tool. This exposes clear JSON schemas to the model, giving the LLM an explicit mechanism to write, update, or remove database entries dynamically while generating its response. Rather than relying on rigid, hard-coded scripts to save data, LangMem equips the agent with the tools to autonomously curate its own relevant facts. Once the user receives their response, the hot path goes dormant and the cold path activates. This asynchronous pipeline executes completely out of band. A background worker spins up and processes the finalized conversation thread. It passes the raw message list into a thread extractor, isolating specific factual assertions and entity relationships from the noise of the chat. To prevent the model from hallucinating false facts, the memory manager forces these unstructured strings through strict schema validation, converting them into typed, uniformly structured pydantic extractions. Before committing these new facts to the persistent store, the manager performs a semantic retrieval of existing memories. If a newly extracted fact contradicts an older one, it resolves the conflict. It updates the existing item with the latest context, rather than blindly appending a duplicate. This active semantic deduplication prevents the vector database from corrupting itself over thousands of sessions, holding token costs down while maintaining an accurate user state. Storing data is only half of the memory equation. For an agent to actually adapt, it must also refine its behavioral logic over time. Periodically, LangMem routes batches of past interactions through a prompt optimizer. A dedicated evaluator model analyzes these historical trajectories, explicitly hunting for instances where the agent failed to execute its goals. Instead of relying on numerical loss functions, the evaluator generates textual gradients. These are detailed natural language critiques analyzing exactly why a specific set of instructions led to a failure state. The optimizer applies these critiques to the agent's core operating instructions, carefully mutating the interconnected system prompts to eliminate the identified errors. By utilizing natural language feedback loops, the system navigates discrete text space to iteratively correct its own logic, eliminating the need for manual prompt engineering. Operating autonomous memory systems in a local sandbox is straightforward. Deploying them across high-concurrency, multi-tenant enterprise environments requires hard boundaries to prevent cross-contamination. LangMem enforces strict namespace isolation at the storage layer. Every memory operation is bound to a parameterized tuple, like enterprise ID and user ID. The underlying store isolates all queries, so agents can only read or write within authorized scopes, preventing data leakage. To manage active execution safety within the hot path, the framework monitors the token budget on every turn. When conversational history approaches limits, a summarize messages function fires. It strategically compresses older turns into a rolling context, rigorously protecting active tool states and vital system instructions from being purged. Namespace isolation locks down privacy across disparate threats, while context compaction ensures execution remains deterministic, satisfying strict production security requirements. When we reintegrate these components, we see a complete, continuous learning runtime. An interaction enters the hot path, querying and logging targeted facts in real time. Once complete, the cold path extracts structured knowledge, resolves conflicts, and evaluates the trajectory to rewrite the agent's core prompts. This split design proves a structural reality. Functional agent memory cannot exist entirely inside a synchronous chat loop. The required latency costs and data bloat mathematically prohibited. LangMem leaves amnesic models behind. It establishes memory not as a static filing cabinet, but as a dual-path engine designed to autonomously personalize, scale, and learn.